So in this video, let us discuss about the amount of energy stored in an inductor. Suppose we have an inductor, let's say an inductor having inductance L, which is connected across an AC source. This is an AC source and this is the inductor. When they are connected, a current flows through the inductor. Let's say I be the current, and the current grows in the inductor from value 0 to a maximum value of, let's say, I0. Initially there is no current in the inductor and the current can grow up to I0. Here the I stands for the current at any instant through the inductor. Now we have, by definition, L is equal to, before that, what happens to this inductor is that when current flows through the inductor, an EMF is, or there is a flux developed across the inductor like this. And let phi be the magnetic flux developed. And by definition, we have inductance is equal to flux developed divided by current. The ratio of flux to the current is, by definition, the value of self-inductance. Now we have phi is equal to Li. Let's call this as equation 1. Now from Faraday's law, we have the EMF induced in the inductance or inductor is actually minus d by dt of derivative of flux phi. Actually, this is according to the Faraday's law. The rate of change of flux linked with a coil gives the amount of induced EMF. Minus sign indicates that this is according to Lenz's law, and this negative sign indicates that the EMF induced opposes the current through the inductor. So we have EMF E is equal to minus, instead of phi you can put Li. So d by dt of Li. Now clearly this L is constant, so you can take that out. Therefore the EMF E is equal to minus L di by dt. So this is the value of the induced EMF. Call that as 2. And now what this induced EMF is doing is, it opposes the current. So in order to maintain the current through the inductor, this source voltage this is the source voltage, it has to do some work. So the work done, otherwise if this source voltage does not do any work, there will be no current flowing through the circuit, because this EMF developed opposes the current and almost eliminate this current. Now the work done by the source must be against this source EMF, against this induced EMF. And we have, by definition, work is equal to power into dt. We have, by definition, power is equal to rate of doing work, dw by dt. So work is equal to power into dt. Again, this work has to be against this EMF, so I have to put a minus sign. Now substituting, we have dw is equal to, again, power is actually voltage into current, dt. Now we have dw is equal to minus, I can substitute minus L di by dt instead of E, that is minus L di by dt. So that's our EMF, then the current I, now the dt. Clear? So this will become dw is equal to, minus and minus will become plus. So L di into I, see this dt and dt will get cancelled. Implies the work done dw is equal to Li di. I can rearrange and write like this. Call this as equation number 3. Now to get the total work, that is the total work done, let's write that as W, that must be, here the variable is di and I varies, that is current varies from 0 to I0. So I have to take the lower limit as 0, that is current varies from I equal to 0 to I equal to the maximum value I0. Now L I di. Therefore W is equal to, clearly this L is constant, integral 0 to I0 I di, and that is L times I square divided by 2. Now put the lower limit and upper limit. Here integral x dx is actually x square by 2 plus some c. We don't have to care about this c because this is a definite integral. So integral I di equal to I square by 2. Now first put the upper limit, that is I0 square by 2 minus 0 square by 2, then the lower limit. So this is equal to L I0 square by 2. So work done by the external source is actually W is equal to half L I0 square. And this work is stored as energy. Work is stored as energy in the inductor. So the energy stored in the inductor is E is actually half L I0 square, where I0 is the peak value of current. Clear?